Hello everyone, so we're gonna do 9.10, which is still talking about volume and surface area of 3D shapes a little bit, but now we're gonna talk about similar solids, and you might have remembered in Unit 6, I believe, was all about triangle similarity, and this is kind of that same concept. Similarity in geometry always refers to shapes or things that have the same shape but not the same size. So solids just refers to like a 3D shape, and so we can talk about a similar pyramid or similar prisms. Two solids are similar if the ratio of their corresponding linear measurements are equal. And so we're going to be talking about ratios again, which is something that was brought up in Unit 6 whenever we would kind of work with proportions. Those were examples of ratios. When we say linear measurements, there's a couple things that we're talking about, and we'll list them out here. All the different types of linear measurements could be considered like length, width, height. You could also say the slant height is a linear measurement. And you could also say perimeter is a linear measurement. Radius, diameter, and circumference. Notice how we're excluding area, surface area, volume. Those wouldn't be considered linear measurements, but all of these would count. So the directions for these examples say to determine whether the solids below are similar. If yes, give the scale factor in simplest form. So we're going to be given a couple pairs of solids, and then we have to determine whether they're similar by comparing their linear measurements and making ratios. So for example, we want to compare the same measurement. This 12 is like the height of the pyramid, so I want to compare that to the height of the other pyramid, which is 3. So the ratio is 12 to 3, or 12 over 3. I am going to look at this measurement now, the 8, that is compared to the 2 on the other shape. And then the last ratio would be the 20 and the 5, so 20 over 5. So now we have to determine whether all of these ratios are equal. And if they are, then we can say, yes, they're similar. So you would just simplify these ratios as much as you can. Like 12 over 3 would really just simplify to 4. 8 over 2 would also simplify to 4. And 20 over 5 would also simplify to 4. So all of them equal 4. So let's say, yes, they can be considered similar. And if yes, we have to give the scale factor in simplest form. So scale factor is like a fraction that tells us what their ratio is. And so because all of these came out to 4, really they would be 4 over 1 when you simplify the fractions. And so our scale factor is going to be 4 to 1. Remember, ratios and fractions are pretty much the same thing. It's just that when we put it 4 over 1, and as a ratio, that would look like 4 colon 1 or 4 to 1. Okay, so let's look at number 2. For these rectangular prisms, we have to compare the same measurements on each side. So I'm going to do the 6 on the bottom and compare that to the 10 on the other shape. Then we have this 6, which matches up with the other 10 as well. And then the height is going to be 8 over 12. Okay, so let's simplify these. You could use your calculator to simplify these if you don't remember how to simplify fractions, but 6 over 10 just simplifies to 3 over 5. We have the same thing over here. And then 8 over 12, the number 4 goes into both of them. 4 goes into 8 2 times, and 4 goes into 12 3 times. So this is 2 over 3. And notice how they're not all the same. We have 2 3/5 and then 1 2/3. They all have to be equal in order for us to claim that they're similar. So for this one, we're going to say no. Number 3, we have 2 cylinders, and we have the diameter on the one on the left, and then the one on the right only gives us the radius. So we want to compare the same types of measurements for each one. So if we have the diameter on one of them, we want to make sure we have the diameter on the other. If the radius is 10, that means the diameter would be 20. So when we compare the diameters and make a little proportion or fraction, we're going to have 24 over 20. That's this over this. And then for the heights, we're going to have 30 over 25. And let's simplify these. 24 over 20, the number 4 goes evenly into both of these. So 24 divided by 4 is 6, and 20 divided by 4 is 5. So we have 6 over 5. For 30 over 25, the number 5 goes evenly into both of them. So 30 divided by 5 is 6, and 25 divided by 5 is 5. They're both 6/5, so we would say yes. And then our scale factor would be 6 to 5. So there's a little bit of a different process if we're comparing the volume and surface area of two different solids and then trying to determine whether they're similar or not. If we're comparing volume and surface area, just remember these guidelines. If two solids are similar with a scale factor of A to B, so that would be like any of these scale factors that we just found, then their volume and surface area ratios are as follows. For surface area, it would be A squared to B squared. So if our scale factor was 4 over 1, we would take 4 squared to 1 squared. 4 squared is 16, 1 squared is 1. So the new surface area ratio would be 16 to 1. Volume is A cubed to B cubed. So we just take whatever our scale factor is and then cube each one. So I'll do a couple examples of this just so that you can see how we convert them. The directions say identify the scale factor or ratios for each pair of similar solids. So we already know from the get-go that these solids are similar to each other. We don't have to determine that. The thing that we should start with is looking for the scale factor and then finding out what the surface area ratio would be, what the volume ratio would be. So you can find the scale factor pretty easily just by comparing two corresponding sides. So 10 over 5, that simplifies to 2 over 1. So the scale factor is 2 to 1. So we can find the surface area ratio by remembering A squared to B squared. So I'm just going to do 2 squared, which is 4, and then 1 squared, which is just 1. We could also find the volume ratio kind of similarly, except now we're going to do A cubed and B cubed. So 2 cubed, or in other words, 2 times 2 times 2 would be 8, and then 1 cubed would just be 1, so 8 to 1. Let's do a couple more of these just so that we get a good amount of practice. We know that these two cones are similar. We just need to start by finding the scale factor. So if we compare these, 4 over 6, that simplifies to 2 over 3. So the scale factor is going to be 2 to 3. And now I can find the next one. So remember, for surface area ratio, it's A squared to B squared. So 2 squared is 4, and 3 squared is 9. So the surface area ratio is 4 to 9. For the volume ratio, it's A cubed to B cubed. So 2 cubed is 8, and then 3 cubed, or 3 times 3 times 3, is 27. So that's how you find the surface area ratio and the volume ratio given your scale factor. In other cases, you might be starting with the surface area or the volume. When given surface area or volume, always find the scale factor first. And so you pretty much know this ratio. Like if you are given the surface areas, we know that the surface area ratio is 25:4. We could then fill out the rest of this. We could go to finding the volume ratio, but what this is saying is that we first need to work backwards to find the scale factor. And the way that you would do that is think about, well, if the surface area ratio is just a squared to b squared, then the scale factor is just going to be the square root of both of these. So if you square root 25, you get 5. And then if you square root 4, you get 2. So the scale factor is 5:2. Then you can use that to help you find your volume ratio. The volume ratio is going to be a cubed to b cubed. So we have to do 5 cubed, or 5 times 5 times 5, which is 125. And then 2 cubed, 2 times 2 times 2 is 8. So 125 to 8 would be our volume ratio. Number 7, they're starting us off with the volume. So we could find out what the volume ratio is just by comparing these two numbers. We're going to do 162 over 384. This is a really big fraction, which can be simplified. You could use your calculator to do this because these numbers, I don't really know exactly what could go into both of them. So I'm just going to type that in the calculator to simplify, and it comes out to 27 over 64. And I'm going to write that over here. So this is my volume ratio. And remember, before doing anything else, work backwards to find the scale factor. So if our volume ratio is just a cubed to b cubed, to find out what the scale factor given the volume ratio, you would just do the opposite. The opposite of cubing something is taking the cubed root, and there is a way to get a cubed root function on the calculator, and I'll show you guys how to do that in class. But basically, the cubed root of 27 is like, what number can you multiply by itself 3 times to get you 27? That's going to be 3. 3 times 3 times 3 is 27. The cubed root of 64 is kind of the same thing. What number can we multiply by itself 3 times to get 64? The answer is 4. 4 times 4 times 4 comes out to 64. Now you can find the surface area ratio. If the surface area ratio is a squared to b squared, then our scale factor is going to be squared. 3 squared is 9, and 4 squared is 16. So the surface area ratio is 9 to 16. Number 8, we're starting off with surface areas. So let's use these to give us our surface area ratio. These are pretty big numbers, so I have a feeling that we can simplify this. And we can. This comes out to 64 over 25. And I'm going to write that here next to surface area ratio. And remember, you have to work backwards first to the scale factor. Don't go finding the volume ratio after identifying what your surface area ratio is. We're just going to square root both of these now to get the scale factor. So the square root of 64 is 8. The square root of 25 is 5. And now we can use these to find the volume ratio. We just have to do a cubed to b cubed. So a cubed, you're going to type that in the calculator most likely, is 512. And then 5 cubed is 125. So there's a few questions where they won't give you any diagrams. You just have to read the problem, like numbers 9 through 12. Number 9 says solid A is similar to solid B. The ratio of the height of solid A to the height of solid B is 7 to 3. Find the height of the volume of solid A to solid B. So this is kind of putting everything together. It tells us that two solids are similar. It tells us the ratio of the height. So if you are talking about a linear measurement, remember we listed off all of our linear measurements, height was one of those, that means that you have the scale factor. And we represent a scale factor with A to B. This is 7 to 3. The question is telling us to find the ratio of the volume. So the ratio of the volume is found by taking a cubed to b cubed. So we just have to cube the 7 and the 3. So 7 cubed, or 7 times 7 times 7, is 343. And then 3 cubed, or 3 times 3 times 3, is 27. And this would be our answer. That's going to be the volume ratio of solid A to solid B. Number 10 is talking about cone A and cone B. It says that the ratio of their surface area is 16 to 1. So this ratio of the surface area is represented by a squared to b squared. So we can write that and set that up as 16 to 1. We want to know what the ratio of the radius is. Remember, radius is a linear measurement. And so if you want to know the ratio of the radius, you're essentially being asked to find the scale factor, or a to b. So if we want to work backwards to find the scale factor, if we know the surface area ratio, we just have to square root both of these. So the square root of 16 is 4, and the square root of 1 is just 1. So the ratio of the radius, or the scale factor, is going to be 4 to 1. Number 11 tells us that two cylinders are similar. Cylinder A has a diameter of 24 feet, and cylinder B has a diameter of 34 feet. So they're not telling us what the ratio is, but we can find that really easily if we know that diameter is a linear measurement. So I'm going to say 24 over 30 and simplify that. So the number 6 goes into both of these. 24 divided by 6 is 4, and 30 divided by 6 is 5. So if we have the ratio of the diameter, that's like our scale factor. So I'm going to say that A to B is 4 to 5. And the question is, what is the ratio of the volume of cylinder A to cylinder B? So volume ratio is found by taking A cubed to B cubed. So now all we have to do is cube our scale factor. 4 cubed is going to be 64, and 5 cubed is going to be 125. So this would be our answer, the 64 to 125. Number 12 says Pyramid A and Pyramid B are similar. Pyramid A has a volume of 648 meters cubed, and Pyramid B has a volume of 1,029 meters cubed. What is the ratio of the surface area of Pyramid A to Pyramid B? So we are given the two volumes. So we can find the volume ratio based on the measurements that they gave us, the 648 and 1,029. So let's make this into a fraction, simplify this so that we know what the volume ratio is. When you simplify that, you would find it to be 216 over 343. And this is our volume ratio. Volume ratio is represented by A cubed to B cubed. So I'm going to say this is 216 to 343. And we want to know what is the ratio of the surface area. So if you have the volume ratio and you want to find the volume of the surface area, similar to what we were doing in these types of problems, first you have to find what the scale factor is. So we have to find what our A to B would be. So I have to take the cubed root of each of these, like that. And I would just use the calculator for that. So the cube root of 216 comes out to 6, and the cubed root of 343 comes out to 7. Now we can find the ratio of the surface area, which is represented by A squared to B squared. 6 squared is 36, and 7 squared is 49. So the surface area ratio is 36 to 49. So that's the lesson on similar solids, 9.10. There are some more notes for more practice in case it's still a little bit murky. There will be some more stuff after this, so it's important that you understand how to work with similar solids.